Welcome to another online lesson, calculus students. We are going to look today at writing vector equations for lines in space. And what I mean by lines in space is 3D vector equations. We want to be able to apply our knowledge from 2D vectors and those equations to now write vector equations in 3D. So terms and notation. There is a old show from the late 70s, and now they've been revived in many movies, called The Muppet Show, and they used to have a bit called Pigs in Space. Well, today we are learning about lines in space. And so they call them lines in space because they're 3D, meaning they're not on a plane, they're not trapped on a flat surface. They can go anywhere. They can go forward, backwards, up, all of these sorts of things. And you'll notice our vector equation is very similar. We've often used the form vector r, which is a position vector or a final position vector, equals our starting position plus a scalar variable representing often time times our directional or velocity vector. Well, that's what we have here. Again, we have another location or a value of a point on our line. We have the starting point or some relative position on our line, our scalar variable, and then our directional vector. Once again, we can break these up into parametric equations, and we can see that here, that the x is going to have, this x sub 0 plus a times t, and then the y sub 0 plus the b times t, and so on and so forth. So this time we have 3 parametric equations rather than just the 2 that we had in 2 dimensions, which makes sense. And then here we've got a little bit of algebra, which probably won't come up, but they call these Cartesian equations, and they are just a rearrangement of our parametric equations now in terms of the variable rather than being in terms of t. So all the things that we used to be able to do with 2D vectors and 2D vector equations, we should be able to do as well with 3D vector equations. So the first thing we're doing is we're just writing a vector equation. It says find the vector equation and parametric equations of the line through the ordered triple 1, negative 2, 3 in the direction of 4i plus 5j minus 6k. So that's written in unit vector form. I'm probably going to write my answer both ways. To start with, we are going to use the form r equals a plus t times b or b times t. Again, r is our variable or final resting position vector, So we can call that x, y, and z. Then we have our starting position. Well, they gave us a point. So we're going to use that as our starting position. 1, negative 2, 3. And then we have our scalar of t. We could really use any variable, though that's the standard one. And then we're going to use this directional vector, which has an x component of positive 4, a y of positive 5, and a z of negative 6. And voila, I have written a vector equation. We're now going to rewrite that using unit vector notation. So I'm once again going to start off with r. I don't want to write all those variables with i's and j's and things like that. So I'll just say r is equal to, and then I'm going to take this guy here, my second or my first position vector with values in it rather than variables, and I'll say I have a single I minus 2j plus 3k. And I'm going to use parentheses just to group that to show that was one vector. It makes it easier to look at when you're all said and done. Plus, you can put the t in front or behind. I'm going to put it behind because I'm more comfortable putting numbers before variables. And so I have my 4i plus 5j, and then minus 6k, which I just barely had room for, all times t. As you can see, that first set of parentheses is optional. The second set of parentheses can be removed if you distribute t to everything. That's sort of a standard way of writing it. Allows us to see our 2 separate vectors, and we're written in unit form. All right, last but not least, it tells me to break up my parametric equations. So we're going to have 3 of them. We'll have one for x, one for y, and one for z. The x we can see right here is equal to 1 plus 4 times the t. And so I've got 1 plus 4t. Same idea for the y. We start here at the y and see what that is equal to. And we have a negative 2 plus 5t. And then last but not least, 3 minus 6t, because we had the negative 6 here. So I just distributed that to the t, negative 6t. Parametric equations. And we've seen uses for those when we're trying to solve systems of equations or set different lines equal when they intersect and things like that. All right, this one asks us to find the parametric equations of the line through A and B, and they give us ordered triples for each of those. So we're going to need a few things here. We need a position vector. Again, we're going to be writing, I like to start with my vector equation and then break it apart. So we're going to start with R equals A plus B times T, or the other way around is fine as well. And so we've got our X, Y, and Z equal to a starting point. Well, starting point, we could use A or B. Just to make life easy, I'm going to use A, 2, negative 1, 4. But if you put the B in there, your answer is just as correct. You got to use one of those 2 points, either A or B. Because a line doesn't really start anywhere. It's not a word problem where we're actually starting in a specific spot on the line. We just need to define the line by saying, yeah, it goes through this point. So either one of those points is just fine. And now we need our directional vector. In order to create a directional vector, we have to have a vector, and we don't have one. We have points. So if I want to go to AB, I would subtract backwards, and I would start with my B values, which were negative 1, 0, 2. And then I'll minus my A values, which is minus 2, minus negative 1, and minus 4. And we end up with negative 3, positive 1, and negative 2. So that is my directional vector. I've got negative 3, positive 1, negative 2. And I have written my vector equation. Now, are there other vectors that I could use for that direction? Yeah, I could take any scalar. Like I could multiply all the values of this last vector here by a 2. And I would have negative 6, 2, and negative 4. And that would still be in the same direction, and it would still be the same line. Or I could have actually used the vector BA instead, and it would just be the reverse. But remember, a line doesn't go in one direction. It goes in 2 directions. So it really doesn't matter. We can plug in negative values for t, and we can still get every single point on here expressed through our x and y and z values. I still haven't answered the question, though. It said write parametric equations. So I need 3 equations, one for x, one for y, and one for z. Our x is going to be 2 minus 3t, just like we did before. Our y is going to be negative 1 plus a single t, and our z is going to be 4 minus 2t. Once again, I'm getting these for the x. We take the 2 plus the negative 3t, or minus 3t, and for the y, we take negative 1 and the 1t, and so on and so forth, doing the same thing for z here, again, including the t every time. It gets a little messy as I do that. I'm going to finish with this last example and step it up in difficulty just a little bit. We've looked in previous classes about shortest distance. We always said the shortest distance between a line and a point is a perpendicular, sometimes referred to as an altitude in geometry class. Here they're referring to it as something else. They say find the coordinates of the foot of the perpendicular from point P to the line with the following parametric equations for x, y, and z. So if I had to draw a picture here, we've got point P, which is negative 1, 2, and 3. And then we have some sort of line coming across here. And we want to draw or have a perpendicular that comes across here. And we want to know what are the coordinates of this foot, or the bottom of it, or the place where it meets the flat surface. Think about your feet. That's where your body meets the ground. If you think of this line here as the ground, and then we want to know what's this point that'll be the foot of this perpendicular right there. So we need... anytime we talk perpendicular in vectors, we know that our dot product is going to equal 0. So we're eventually going to have some sort of equation equaling 0. And we need 2 vectors. What we first want to do is actually start by writing our vector equation. We have x, y, and z. I'm going to take all my parameters here and then put them back into a vector equation form. So my constants are -1, -4, and 3. And then my coefficients of t are listed here, 2, 3, and 1. All multiplying t, got a plus sign there. All right, so I've got my vector equations. Once again, these x, y, and z values represent any point on this line. There's an x, y, and z for each of these points that I'm drawing here, infinitely many of them. And there is one specific x, y, and z value. Oh, comma, sorry. Let's try that again. There's one specific x, y, and z value that is going to be located such that, oh, let's try it one last time. Located such that it's right at the foot of this perpendicular. X, y, and z. All right. And I need to create another 2 vectors so that I can do my dot product. One of them we will get between this value here, this xyz value, my foot of my perpendicular, and point P. If I'm starting at this point, I'm going to call it F for foot. And I want to now find a vector FP. I subtract backwards, starting with P. And that would be -1 minus x, 2 minus y, and 3 minus z. So that is one of my vectors. I have another vector that goes in the direction of this line. I don't need to use x, y, and z because I already know the direction of the line. It's given here in this equation. So I'm going to take this vector that I created with f and p and do the dot product with this directional vector or velocity vector from my original parametric equations, 2, 3, 1, and that dot product should equal 0. Now, we had mentioned before that we can't do the dot product here because there are 3 different variables. We need to now get these in terms of t. Well, you'll notice with these parametric equations, I know a value of x that's in terms of t, and then I can do the same thing for y in terms of t, and finally my z, again, in terms of t. So I'm going to rewrite this dot product now substituting in place of x, y, and z so that I don't have the 3 different variables. So instead, I only have one variable of t. Might need a little more room there. So I take the -1, the 2, and the 3 that I just had here. And now instead of subtracting x, I subtract the value 1 plus 2t. And then I subtract -4 plus 3t, which was my y parametric expression, and then minus my z, which is 3 plus a single t. Now I only have one variable. I'm still going to do my dot product here with 2, 3, and 1 and set it all equal to 0. Maybe we can clean things up a little bit. We'll distribute these negatives here. And so I end up with new expressions. A -1 minus this other one will become a -2. Let's give me a little more room. So we'll have -2 minus 2t. And then that was for that first one there. For the second one here, I'm going to do 2 minus a -4, which is +4, which gives me 6. And then I've got to distribute the negative, so minus 3t again. And then finally 3 minus the 3 gives me a 0, and I end up with just t for that one there. I'm sorry, -t. Again, that was after distributing right here. All right, so those, that is my vector, and I've got 2, 3, 1 here, all again equaling 0. Moving on. So now we take -2 minus 2t, and we are going to do our dot product. So we multiply that with this 2 here. So I'll put a 2 in front of that to show that I'm multiplying. And then plus, I've got the 3 times my y parametric equation, which was 6 minus 3t. And then last but not least, I'll take the 1 that I have over here times this -t, which will just be minus t, which is perfect because I only had enough room for that. And that is my dot product. I know it should equal 0. We're still not done because we got to actually clean this up and solve for t. So I distribute my 2. I get -4 minus 4t plus 3 times 6 gives me 18 minus 9t minus a t. Let's look for like terms. My constants, I've got -4 an 18, so that'll become a 14 there. And then my variables, I've got negative 4t, negative 9t, and negative t. Oh my goodness, could this work out more perfectly? I end up with negative 4 plus negative 9 is negative 13, and then one more negative t gives me negative 14 t's, which equals 0. I'm trying to get my t's to one side, so I subtract from both sides. We're going to subtract 14 to get my variables alone. I have negative 14t equals negative 14, and then divide both sides by negative 14, so I can clearly see that t is going to equal 1. Now, is that what it asked me, to find t? No. It asked me to find the coordinates. So now I know what the t value is. We're so close, ladies and gentlemen. We are now going to take that t value and plug it into each of these parametric equations for x, y, and z. So when I plug in my x value, I will have x equals 1 plus 2 times 1, which gives me 1 plus 2, which is 3. My y value is going to be negative 4 plus 3 times, again, my t value, which was 1. And negative 4 plus 3 gives me negative 1. And then finally z, which is 3 plus my t value, which was just 1, which gives me 4. So my ordered triple for the foot is going to be 3, negative 1, 4. Awesome. All right. For homework, problems 5, 6, 7, 8, and number 4. Only 5 problems on page 324 and page 327. 327 asks us to find the angle between vectors, which we've done for 2D vectors. Again, focus on your directional vector, your velocity vector, and then use that dot product formula for cosine. And the others are very similar to the examples we looked at. Until next time, ladies and gentlemen.